Hello, talking today about section 421, which is graphing rational functions that are the form y equals a over 1 minus h plus k. And I just realized that I don't have it set so that I can write on the screen. So I'm going to fix that. All right, here we go. So we're graphing things of the form y equals a over x minus h plus k. So you should remember from before, we've been doing transformations that the k moves your graph up or down, and the h is going to move your graph to the left or to the right, really the opposite of what you would think, and the a is going to be a vertical stretch or compression. And we're going to be doing transformations of the graph 1 over x. So you might remember back from when we did parent functions all the way back in August, that the graph of 1 over x is a hyperbola. So if you made a table, you would have these branches that level off at 0. They level off at the x and the y axis. So when we look at this equation here for g of x, this plus 2 is going to move this graph here to the left 2, and this plus 3 is going to move our graph up 3. So similar to when we have graphed like sines and cosines and we have a vertical shift, how we think about the whole midline is shifting, here it's as though this whole x-axis is going to shift up 3. So over here, I'm going to kind of draw in my new x-axis, and then it's like my y-axis is shifting to the left 2. These are going to be my asymptotes for the graph. So we were asked a bunch of questions here to describe the graph, and one of them are, what are the asymptotes, both horizontal and vertical? So our graph is going to have this shape, and it's going to be like in my new first and third quadrants. It's going to look like this, and it's leveling off at that line right there, that horizontal line, x equal y equals 3. And then vertically, it's getting closer and closer to this vertical line, x equals -2. So when we talk about where are there asymptotes, those are the lines that your graph approaches but never crosses. So we have a vertical asymptote at x equals -2 and a horizontal asymptote at y equals 3. Notice that I'm writing those as equations for lines. I'm not just writing -2 and 3. They represent lines. They should be equations. Okay, we're asked what the domain and the range are of this function here. Domain are your possible x values. And the only thing that x can't be when I look at this graph here is there's this break at -2. So x can be anything except for -2. So I'm just going to write x is not equal to -2. And the range, the y values can be anything except for there's this break at y equals 3 at 3. So our range is anything y but not equal to 3. Right, then we're asked to state the intercept. So this is a sketch. I don't know here. I mean, it kind of looks like it goes through 5, but I don't really know where it goes, right? This is just a sketch. Maybe I didn't sketch it very well. In fact, I know I didn't sketch it very well. It probably could have been coming down a little bit lower here, but it asks for me for my intercept. So that means where it hits the x and the y axis. Like x-intercepts, any point that's an x-intercept, the y value is 0. So to find the x-intercept, I'm going to put 0 in for y. So in this equation here, in place of g of x, I'm going to put 0. And then I'm going to solve for y, or solve for x rather. I'm going to subtract the 3. I don't really love this x plus 2 on the bottom. I'm going to multiply x both sides by x plus 2. So over here, I have -3x minus 6 equals, those cancel, 1. I'm going to add the 6. 7, I'm going to divide by the -3, so x is -7/3. So I have an x-intercept at -7/3, 0. Okay, to get my y-intercept, that's when x equals 0, right? Any point on the y-axis, the x value is 0. So into this equation here, I'm going to plug 0 in for x. So that gives me 1/2 plus 3, or 3.5. Yeah, I really didn't do a good job of drawing this, did I? I should have been coming down a lot lower than I did. But my y-intercept would be 0 3.5 or 7/2. Right, and then we also want to describe the end behavior. So that is, as the x values increase, what do the y values do? As the x values decrease, what do the y values do? We're going to move towards this notation here, the shorthand, so I have to write out the sentence. As x approaches infinity, that means increases, gets really, really big, what do the y values do? As x approaches negative infinity, gets really, really small, what do the y values do? So on this graph, my x values get bigger, bigger, bigger. So as I'm going this way horizontally, my y values are getting smaller, 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 but they're not getting smaller without bound. They're leveling off at this horizontal asymptote of 3. So we would say as x approaches infinity, y approaches 3. And on the other side, as the x values get smaller, 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 I see the y values are increasing, but over time they're getting closer and closer and closer to this horizontal line of 3. So we would say y approaches 3. Okay, so we're going to head towards writing it like this. And then ultimately we're going to get an even more concise notation than that. Now, sometimes you might be given a rational function and it might be written like this. It's not written in that nice graphing form where I can easily tell what the horizontal and vertical shifts are. And so we're going to talk about 2 different ways that we could rewrite this in this form so that we can tell what our h and our k are. So one way is just to use polynomial division. So I can set up a box and I want to divide that x plus 2 into this 3x plus 7. So I have my 3x here, and I think what times x is 3x? So 3. 3 times 2 is 6. And I need my constants to add up to be 7, so I have to add 1. Really, that's it, I'm done. So I'm going to write my answer as the quotient plus the remainder over the divisor. So my quotient here is 3, plus my remainder is 1 over my divisor, which is x plus 2. And if I take this and I rewrite it so that, this is kind of flipped around, so it's more in this form, I could write h of x equals 1 over x plus 2 and then plus 3. So then I would easily be able to say, oh, my h is -2. So that means I'm going to the left 2, and then my k is 3, and going up 3. It's the same equation as what we had up here, just how we could rewrite that to get to it. Now, another way that I could have seen this is by using some giant ones. So we're going to use this idea of, let's say I gave you the number, let's say 20 over 17. I said, write that as a mixed number. You say 17 goes into 20 once with 3 left over, so 3/17. Another way I could see that 20 over 17 is I could split that 20 into 17 plus 3 over 17. I'm doing that because then I'm going to have this giant 1 here. So this could now be split apart. So usually I take 2 fractions with a common denominator and I put them together, right? These are equivalent. Now the reason I did that is because at 17 over 17, that's just equal to 1. So now this is 1 3/17. So I'm going to use this idea to rewrite this 3x plus 7 over x plus 2. It's just an alternative way. You do the polynomial long division or division with the box, or here's another way to see it. Okay, so I am going to split this 3x plus 7 into as many x plus 2s as I can. So I've got 3 x's, so I'm going to have x plus 2, and then another x plus 2, right? So that's so far 2x plus 4. I've still got 3x plus 7 to get to though. Another x plus 2. So x and x is 3x, 2 and 2 is 6. But then I need to have a 1, so that all the constants add up to be 7, all over x plus 2. And then what I can do, and right now you're going to think that's a lot to write out, but once you kind of see it, you don't always have to write it all out. Right now I'm going to split these all up so they're over x plus 2. I know you're like, oh, that's so much to write. But when you do that, these are all 1. 1 plus 1 plus 1 is 3. So this becomes h equals, I'm going to put this in front so I have it in this form here, 1 over x plus 2 and then plus 3. Okay. So some people like doing it that way. Some people prefer to just do the division. Okay, so if I gave you this one here and I said, all right, go ahead and graph this, You could choose whatever method you want. I kind of think the division is faster, but some people might say, oh, I can see I've got, you know, two X's here, and then I could add a 1 to make it next, whatever. There's things that you can do. I kind of just like the division. I'm going with that. It seems faster to me. All right, so this is 2 here. This is -6, but it has a total be -5. So this would have to be a 1. So then I can rewrite this as so this is like 2 + 1 over x - 3. I'm going to write it over here so I can see my h and my k a little bit more easily. Okay, so this is going to move me right 3, and this is going to move me up 2. So that means I'm going to have now horizontal asymptote through y equals 2, and it's moving to the right 3. So I'm going to have a vertical asymptote through x equals 3. And this is just a 1, it's not negative, it's not flipping anything around. So then if it's just a sketch, I don't have a graphing calculator, it's just, trust me, it's really wonky to draw with this pen. I know they look terrible, right? But the idea is that the branches would be here and here. Okay, we're just trying to get a sketch. All right, really, that's it. That is 421 in a nutshell.